Students, in this session, let us discuss about the classification of the gas turbine power plant. Here there are varieties of the criteria by which the plants are classified. So by cycle, the gas turbine power plant is classified as open cycle plant, second closed cycle plant, third semi-closed power plant. Look into the first open cycle power plant. Here, the main components are compressor, then combustor, and turbine, and alternator. Here, the compressor and the turbine are connected on the same shaft to which the load is extracted. Here, the alternator is also coupled with the same shaft. Here, the air is from the atmosphere drawn into the compressor. Then it compresses the air. Here, the compression takes place isentropically. Then the highly pressurized air goes to the combustor where fuel is supplied externally. So by igniting the fuel in the chamber, so the air becomes hot gas. So here, let us we assume that the air follows the ideal gas laws. Here, the hot gas goes to the turbine where it is expands and the work is extracted. So due to the expansion, the turbine is receiving the energy from the expansion of the hot gas. So the turbine shaft starts rotation. Here, the rotational energy is utilized to run the generator. So the power is generated. So from the generator, the gas is let into the atmosphere. So it is called a open cycle plant. So now look into the each operation. So 1 to 2 dash is the irreversible adiabatic compression. Here in the 2 dash, actually the ideal compression process is 1 to 2, ideal isentropic compression process. But actually it is not so. So the 2 is replaced by 2 dash. So 1 to 2 dash is irreversible adiabatic compression. It's also similar to the expansion. 3 to 4 is the ideal expansion process that is in the turbine. And the real expansion process denoted by the 2 to 2 dash to 3. And 3 to 4 dash is a irreversible adiabatic expansion. Okay. Now here we compare the both isentropically real process and ideal process. There is 1 to 2 dash and 1 to. Similarly for the turbine 3 to 4 and 3 to 4 dash. So the assumption is the change in kinetic energy in any points of the cycle is small that compared with the enthalpy change in the plant. Now the flow equation is applied for the air, that is a hot gas. Now we can have the equation. It is a TS diagram. So there are two constant pressure lines, P1 and P2. Here the 2 to 3 is a heat addition at constant pressure, and also 4 to 1 is a heat rejection at constant pressure. So the work input is from the compressor Cp into T2 minus 2 dash minus T1, and heat input to the combustor is Cp into T3 minus T2 dash, and turbine work output is Cp into T3 minus T4 dash. Net work output. Here, the net output is extracted from the turbine, but we go to subtract the compressor work. The reason is, at the time of starting, as we know, the turbine and the compressor are connected on the same shaft. Initially, the compressor is given the power supply. After turbine is brought to the working condition, the compressor is cut off from the electric supply. So some part of the energy from the turbine output is utilized to run the compressor. So we have to separate the compressor work. So that is Cp into 3 minus T4 dash minus Cp into T2 dash minus C1. And thermal efficiency, net work output divided by heat supply. Now we can add we have written the work output, net work output divided by heat supplied in the combustor, Cp into T3 minus T2. Now the next two formula deals with the isentropic efficiency of the compression and expansion. Now, for as per the compression is concerned, the isentropic efficiency in the compression is defined as the ratio of the isentropic efficiency, that is real actual isentropic efficiency input to the actual work required. So in the compressor, isentropic efficiency in the compressor is the isentropic work input to the compression divided by actual work required. Here the actual work input, sorry, isentropic compression is Cp into T2 minus T1, and actual work required is Cp into T2 dash minus C1. Here the formula is the similarly the apply the formula for the turbine. Here it is actually reverse. So as for the turbine is concerned, the isentropic efficiency is the ratio of the actual work output from the turbine divided by isentropic work output from the turbine. So it is T3 minus T4 dash divided by T3 minus T4. In this connection, there are some terms should be desirable to be known. Some terms are pressure ratio. So it is a ratio of the highest pressure to the lowest pressure. Normally, highest pressure occurs at the exit of the compressor, and the lowest pressure is the entry into the compressor inlet. That is a inlet to the compressor. Then pressure ratio it is. Then similarly, work ratio. It is a ratio of the net work output to the total work developed in the turbine. It is a work ratio. Then air ratio. So the amount of air entering into the compressor inlet per unit cycle of net output. So for unit cycle of net output, what's the amount of air that is supplied to the compressor? It is described as the air ratio. Then the combustion efficiency. It is a ratio of the heat actually released by 1 kg of fuel to the heat that would be released by complete perfection combustion. It is a combustion efficiency. Next, let us discuss about the closed cycle gas turbine. Here, the schematic diagram of the closed cycle plant is after the expansion, the hot gas not released to the atmosphere, rather it is given again to the compressor through a heat exchanger. Here, the heat is rejected and the low temperature gas goes to the compressor. Here, the PV diagram, here 1 to 2 is the isentropic compression. So the pressure rises from P1 to P2. Then 2 to 3 is the heat addition in the combustor. So it occurs at the constant pressure P2. Again, 3 to 4 is the expansion process in the turbine. It is also a isentropic expansion. And again, 4 to 1 is the heat rejection at constant pressure. So the 4 to 1 occurs the lower pressure, this constant pressure at P1. Similarly, in the TS diagram, so the points are plotted at the constant pressure lines. Here, 1 to 2 is heat compression. Here is the process is isentropic, entropy is constant. 2 to 3 is the heat addition at a constant pressure. 3 to 4 is a heat expansion process, that is isentropy is constant. 4 to 1 is the heat rejection at a constant pressure. It is plotted in the TS diagram. Here, the 2 to 3 is a heat addition in the combustor process. Here, the volume changes from B2 to B3. That is the increase in volume from B2 to V3 and heat received is MCP into T3 minus T2. Again, 3 to 4 is expansion in the turbine. So the pressure drop isentrically from P2 to P1. Here, the 4 to 1 is the heat rejection at a constant pressure. So again, the volume just decreases from V4 to V1. So the heat rejected is MCP into T4 minus T1. For this closed recycling, air standard efficiency is the work done divided by heat received. Here, work done is the heat supplied to the cycle and heat rejected. Here, the heat rejected is not useful to the plant, so it is to be subtracted. So heat received MCP into T3 minus T2, heat rejected in the 4 to 1 MCP T4 minus T1, heat received CP into T3 minus T2. So upon resolving and simplifying, 1 minus T4 minus T1 divided by T3 minus T2. As for the isentropic process considered, as we know, and the 1 to 2 is the isentropic process, that is in compression, T2 by T1 equal to P2 by B1 or gamma minus 1 divided by gamma. By rearranging the equation, we can get the T2 equal to T1 into Rp power gamma minus 1 divided by R gamma. Rp here is the pressure ratio. Similarly, for isentropic expansion process, we can get T3 equal to T4 into Rp power R gamma minus 1 divided by gamma. And air standard efficiency, as we have written, 1 minus T4 minus T1 and divided by T3 minus T2. So in the substituting the T3 and the T4, we can get, and rearranging and simplifying, we can get the 1 minus 1 by Rp power gamma minus 1 divided by gamma. Here from the expression, the ideal Joule cycle efficiency increases with the pressure ratio. Here, but we cannot increase the pressure in the cycle enormously, but there is an upper limit of the pressure. So the limit is determined by the limiting temperature of the materials of the turbine. So at the point, it is same as the compressor inlet temperature, compressor process itself. So it is a air standard efficiency, and similarly work ratio. Here net work developed divided by turbine work. Here the net work is actually work output from only from the turbine, but it is a useful output. But the compressor work is wasted or exhausted or utilized, so we have to subtract the compressor work, turbine work minus compressor work divided by turbine work. So by switching the formula and rearranging the formula, we can get 1 minus T1 by T3 into Rp power gamma minus 1 divided by gamma. Here again the work ratio increases with the turbine inlet temperature T3, and similarly increases with the compressor inlet temperature T1. Normally compressor inlet is the atmospheric condition. The highest temperature ever practiced in the gas turbine power plant is maximum 1000 degree Kelvin. So this is about the gas turbine power plant classification based on the cycle. The third one is a semi-closed power plant. Here the part of the fluid is confined inside within the cycle, and remaining part is exhausted to the atmosphere. So it is called a semi-closed gas turbine cycle. These are about the classification of the gas turbine cycle according to the cycle criteria. Thank you.